Hello and welcome to another video in my series of videos on control systems engineering. This is Frank Owen, PolyX Engineering, San Luis Obispo, California. Today we're going to talk about the step response of a first order system. This is actually a topic more in the area of system modeling than controls, but it's allied or associated with the field of controls also. So what we're going to look at is we're going to look at the response of a first order system to a step input. A first order system has an ODE that looks like this. It has a first order derivative which makes it first order system, and then also a zeroth order derivative of x in this case, and then on the right, so that's the system part of the dynamics of the system. And then on the right we have a forcing function. We call this the exciting function because it's what makes the system move. And we can have all sorts of exciting functions to drive any system. But in this case we're going to have a step response. And UT shown here is a symbol for a unit step. And we simply multiply it by a constant, which gives us a step of a different size. So the properties of u or of t are that it's 0 before time t equals 0, and then after that it's 1. So the entire product here, f0 times u of t, is at 0 before t equals 0, and then at t equals 0 it jumps up to f0. So we're going to assume that the system starts at rest. When you excite a system, often you have it just sitting still there, and then you apply a function to it at time t equals 0. If we take the Laplace transform of this equation here, we take the Laplace transform of each individual piece, we get this expression here, shown here. You need to look at a Laplace transform table to see what the Laplace transform of a derivative is, and then Laplace transform is linear, so a constant times a function is just, when you take the Laplace transform of that, you get the constant times the Laplace transform of that function. And then our forcing function, again, is f0 times ut, and f0 is a constant, it comes outside, and the Laplace transform of the unit step function is 1 over s. So we wind up with this expression, or this algebraic expression in s, rather than an expression in the time domain that involves derivatives. So basically what the Laplace transform does is it converts an expression that expresses a physical law in the time domain into an algebraic expression in the s domain. Of course, what we're after here, as far as a solution goes, is we're after x as a function of time. We're not going to get that from the Laplace transform version of the system. What we can do is we can solve for the Laplace transform of x as a function of time, and that's a step in the right direction. We use partial fraction expansion to solve this problem. I don't think I've done it yet, but I will produce a video on Laplace transforms and how you do partial fraction expansion. I don't want to go into that here, but basically there's algebraic theorems that say you can break a function like this up into a sum of components. And this goes through the partial fraction expansion and how you do it. I don't want to get into the details of that here, but basically well, I don't want to get into the details of it here, so I'm just going to continue and let us do it. We're going to let s go to 0, and actually when we do this, we wind up with an expression for a, which was one of the constants on the right-hand side, capital A. And so capital A is equal to f0 over a. We repeat this procedure again for the other part of the other component in that sum. Again, I'm not going to go into the details of this. I'll produce a video at some point on partial fraction expansion but I don't want to get bogged down into the details of that at this point. We do some multiplying and crossing out, and actually we solve for the other constant that had been in that sum, capital B. And so we find out that capital B is equal to F0, negative F0 over A. And I have details of the partial fraction expansion in my textbook, Control Systems Engineering, a Practical Approach. You can find the details there if you order the book, and again, I'll probably produce a video on on that procedure, partial fraction expansion, in the future. Now, so what we have here is we've converted the expression. Oh, excuse me. We've converted the expression that we had solved for x as a function of s in the Laplace domain and gotten this function, and we've converted it now into a sum, or actually it's a difference of two components. The negative sign came in the partial fraction expansion. And so what we need to do now is, like I said before, we're trying to get x as a function of t, not x as a function of s. So we have the Laplace transform of the thing that we're after, and we have to do the reverse Laplace transform and go from the s domain back into the t domain. It's actually fairly easy to do. We do this component by component. So we do the reverse Laplace transform, and we get x as a function of t here. And then we look in the Laplace transform table and see if we can find expressions that have this form. Actually, we have a constant up here in the numerator, which we could pull out because, once again, the Laplace transform is linear. And so we have this constant times 1 over s. And in the Laplace transform table, there's an entry for 1 over s. It's just the unit step function. And then over here, we have a constant, and we'll include this negative f sub 0 divided by a. That's a constant. And then we have 1 over s plus a. And there's an entry for 1 over s plus a in the Laplace transform table. It's just e to the minus at times the unit step function. So if we use these entries in the Laplace transform table and do a reverse Laplace transform, on the left, when we do the reverse Laplace transform of x of s, we just get x of t. We had this constant here for both terms, so we're just simply going to pull it out of all of the terms. And then we have ut times 1, that came from this expression here, minus ut times e to the minus at. Okay, and actually in the table it's a, and in our example it's a2, so that makes it very convenient. So we wind up with this expression of x as a function of t, and basically this is the time function or the time history of a for any value of t. With the ut in here, we can see before t equals 0, this is going to be 0, and so it'll just kill everything over here off. And after t equals 0, this will be 1, and so we will have f sub 0 over a times this expression here. Let's look at that in a little bit more detail. There's the expression, and I've just described this. So it's talking about it again. Before t equals 0, then that's 0, and it kills it off. At t equals 0, so at t equals 0, what happens is that u of t changes from 0 to 1. So before 0, it's 0, but at 0, it jumps up to 1. So let's look at it. At t equals 0, e to the negative at, t is 0, so e raised to the 0th power, anything raised to the 0th power is 1. So this becomes 1 at t equals 0, and this becomes 1 at t equals 0. So what we can see is we'll have 1 minus 1. So x of t at t equals 0 starts off at 0, because this is 1 and this is 1 also at t equals 0. So it'll start off at 0, which I've just said. And then let's look at what happens in a little bit more detail. As t increases, when t goes to infinity, because of this negative sign here, what happens is that this number becomes smaller and smaller and smaller. So as t goes to infinity, e to the negative at goes to 0. So this term right here dies off. It's 1 at the start, and then it drops down to 0 exponentially. And because this term dies off as time goes on, it's not part of the steady state solution, as we say. It's the transient part of the solution. Transient meaning that it's there at the first, but then it goes away during the course of t increasing to infinity. And so what happens is that at x equals infinity, this is gone. It's 0 here. This is 1. This, of course, is 1 because t is greater than 0. So the final value that we approach is f sub 0 divided by a. So the initial value, as we've shown before, of x sub t at 0 is 0. And then the final value of x sub t at t equals infinity is f sub 0 over a. And the part that remains of the solution, not the part that dies off, but the part that persists, is called the steady state part of this solution because it persists over time. Okay. Now, another interesting value of t is when t is equal to 1 over a. Notice what happens. That's a positive value, so this will be 1. But what happens here is we wind up with e raised to the minus a over a. So it's e raised to the minus 1. And e to the minus 1 is 0.368. So when we subtract 0.368 from 1, I think, yes. When we subtract 0.368 from 1, we get 0.632 times x to the infinity, which was the f0 over a. So let's see, I think I have some slides that explain this. At t is equal to 1 over a, the first order step response has gone from 0 up to 63.2% of its final value. And we call this 1 over a t, the time constant. And it's a measure of how fast the system is. How long does it take the system to get to this 63.2% of its final value? And as you'll see, as you study more controls, you have some systems that are very, very quick, like an electronic system might be milliseconds in responding. And then you have systems that are very, very slow. A thermal system can have a time constant of hours. So they all have the same expressions, but the scale of time that different systems have as a characteristic, it can be different. Generally, mechanical systems are slower than electrical systems because of the mass. Thermal systems are slower than most mechanical systems because it just takes time for things to heat up and cool down. Now, I actually have gotten the expression that we had for x as a function of t and plotted it in Excel. So basically here, what I've done is I've plotted it from t equals 0 to t equals 2. And simply gotten that expression, f sub 0 over a. I've picked a value for f sub 0, just said it's going to be equal to 5. And then a, I've given it a time, 1 over a is a time constant, so the time constant is 1/3 of a second. And using that expression with these inputs for t, I came up with these answers for x sub t. That's the response of x sub t, and then plotted these as this curve here. You can actually look and see this is just a bunch of little straight lines is what it is. And then the other thing that I did was I calculated 63.2% of the final value. Let's see, the final value, it's f sub 0 over a, so it's 5 thirds. So that'll be 1.67. And then 2/3 of that I've calculated. I don't have that number right here in front of me, but It's a little bit over 1. Maybe it'll show up later on in this presentation. So this value here, this level here is 63.2% of the final value, 1.67. And so I draw that across there, and actually what we'll see if we look closely at what this time would be, it would be 0.3333 because the time constant is 1 over A. So 1/3, and that's 0.333. So it takes 0.33 seconds for the response, the first order response, to reach 63.2% of its final value. Okay, now I've already described these things. Okay, 1.67, I've already described all of these things. So sorry about that it's not so coordinated. What happens here also that's worth noting for a first order response is that it starts off with a rapid increase, but as time goes on, the slope of this curve gets less and less and less until it finally flattens out to have a slope of 0 in the steady state. So it starts off quick, responds quick, always slower until it reaches a steady state value, and then it quits changing altogether. It goes to a new equilibrium state, we say. It was at an equilibrium state of 0, and now it's at an equilibrium state of 1.67. Okay. Well, that's not correct. 63% of 1.67 is not 3.16, so I'll have to correct that. Sorry about that. Okay, and I've described this also. The transfer function of a system is defined as the output over the input, and in this case the output is x and the input is the forcing function itself. So the transfer function is just a ratio of those two. If we go back to the expression on slide 2 for x, this is the actually the Laplace transform of the ODE, and then we solve for x as a function of s. So what we can do, we found out that this is our output, this is our input here, and if we perform this algebra here and divide through by f0 over s, you'll see that we get this. We can manipulate this. Oftentimes what you want in a transfer function is you want the constant value in the denominator to have a value of 1. So what we can do is we can divide the top and the bottom by a, and if we do that we get this expression here. And for a first order system, we have two constants that describe it. We've already talked about the time constant, which is the time that it takes for the system to reach 63.2% of its final value. But then we also have a value called the steady state gain. And what the steady state gain tells you is that if you put in, for instance, a unit step function, then the final value that the system will go to will be this value here, k. Okay, I've just described this. Okay, so when you get this constant term to be 1, the coefficient of the s term is the time constant. That's 1 over a. And the numerator is the steady state gain. Now in this case, both the steady state gain and the time constant are 1 over a. That's purely coincidental for this case. So that's not normally the way things are. Okay. Again, more details of what I've talked about here are contained in my book, Control Systems Engineering, A Practical Approach, which you can order from me for $25 plus shipping and handling. And you can order it simply by sending me an email to fowen@polyxengineering.com. And that's all. Thanks for watching, and I hope you continue to watch, and I'll talk to you in another video.